Welcome again to the Illinois EPA Office of Energy, Public Water Infrastructure, Energy Efficiency Programs webinar series. This is the second webinar in our spring series. And of course, we're always happy to have you here with us today. So keep saying hi in the chat and let us know where you're coming from today. Whoever said they were from Florida, bring some warm weather up here for us when you come back. So my name is Cassie Carroll. I am a program manager or director here at CDAC. I also work with CDAC's technical director, Sean Maurer, who's here today to deliver this program to you all. So before we get rolling, just wanted to say a couple Zoom housekeeping items. So please feel free to use the chat throughout the day today. We'll post questions in the chat and try to see what you're seeing on site at your treatment plants. If you have questions, please share them in the Q&A box throughout the presentation. So we'll have time for Q&A at the end of our session. So we'll have a nice time for discussion. So please send us those questions when you think of them. Also, we do have the CEU course number for this event. So the CEU course number and participation certificates will be available tomorrow and be sent out to all attendees, along with the recording of this session and the presenter slides. So we were really excited to have that in hand and get those to you swiftly. So thank you to the Illinois EPA Bureau of Water for those course numbers. So today's event focuses on VFD application for water treatment systems. So we'll talk about today how you determine if a VFD is a good application for your raw water or high service pumps. So we'll walk you through kind of the understanding of VFDs, pump affinity laws, and how to understand the interactions between pumps and system curves. So speakers today will really help provide a foundation for estimating potential savings in VFDs in your facilities, and we'll hear from the City of Highland Park on how they are applying VFDs across their municipality. So today we have three speakers. We of course have Sean Maurer, our technical director here at CDAC. We have Donald Jensen, who is the superintendent of water production at the City of Highland Park. And we have Matt Johnson. Thank you for filling in on short notice. He is a senior applications engineer at Xylem. So today's webinar will be an hour and we'll provide one CEU hour for this event. All right, so we are with CDAC, the Smart Energy Design Assistance Center, and our goal is really to reduce the energy footprint of Illinois and beyond. So we're one of two partners as part of the Illinois EPA Office of Energy's Public Water and Infrastructure Energy Assessment Program. We also have ISTC, the Illinois Sustainable Technology Center, as a program partner. So Bill and his team over at ISTC really work to encourage and assist citizens, businesses, and government to prevent pollution, conserve natural resources, and to reduce the waste and protect human health and the environment of Illinois and beyond. So really, we're the two program partners. So if you work with us to get an assessment of your plant, technical assistance to identify energy savings, you'll hear from one of our organizations as a part of this program. So I am actually going to turn it over to Sean to talk a little bit about the energy assessment program, what it does, and the value you can gain from getting an assessment at your plant. So Sean, thanks for being here today.
Well, thank you, Cassie. So kind of a quick high-level overview of our program so we can get to the important content. The PWI program with the EPA Energy Office that we participate in is a no-cost energy assessment program for publicly owned water facilities. That includes wastewater and water. When we come out to your site and do an assessment, we're going to generate a report from you, and that report's going to detail issues that we noted on site, issues that we discussed with the operators, potential cost savings from correcting those things, the payback period and economics involved in those. So you can try to start working with your budget committees and planning out implementing those projects through the future. We're a little bit behind on the numbers here, but so far 160 total assessments since 2018. That was what we had at the start of the program year. We're coming up towards the later half of it now. And then $3,400,000 in total cost savings identified, and around, I think we're getting close to $750,000 in implemented savings. But the first step is you have to apply. So you can go to our website, Smart Energy Illinois, smartenergy.illinois.edu/water. There's a button there to click on to fill out an application form, lets us know you're interested, confirms that you're a publicly owned facility, you're in the state of Illinois, so that you qualify for the program. Once we have that form from you, we'll reach out with a phone call and we'll go over some more detailed information about your plant, give us a little bit of an idea of what we're going to be looking at when we get out there. So we'll talk about, do you have pumping systems? Is it for water plant, is it an open cell or an open loop system or a water tower system or closed loop system? And we'll start coordinating data collection with you. We'll need 2 years of utility bills and 2 years of your DMRs for wastewater plants and monthly operating reports for water plants. And sometimes we can work with your utility to pull that information, make that easier on you, so you're not having to network with your city clerk or whoever's managing the bills to get all that information pulled together. So we try to make that process as easy for you as possible. Once we have that more detailed information, we'll do some initial benchmarking. We'll schedule a site visit for you. The first thing we'll do on that site visit is go over that initial benchmarking, let you know where you stand relative to other water treatment facilities in the state of Illinois and at a national level. Site visits are usually 2 to 3 hours. We'll walk through the facility. We'll take pictures of your equipment, process operations. We'll go over any SCADA systems, data trends that you might have. We'll incorporate all that information into our reports and our analysis. And so 1 week after our site visit, we'll turn around a short list of the things we're looking at including in your report. And what we're looking for there is that you can provide us feedback. Is there something in that report you've already looked at, determines not cost effective? We can trim that out of the report. Is there something we didn't list on there that you want to see? That way we tune the report to what you want for your facility. And then another 6 to 8 weeks after that, we actually get the report back to you. And then we'll follow up with you periodically. A couple of weeks after you get the report, we'll touch base with you, see if you have any questions, were there any errors, things we might need to correct. You need help connecting with utilities or grant opportunities, things like that to help your projects move forward. And then we'll probably check in with you on a quarterly basis or so, a couple times a year, just to see where you're at and check on implementation and progress at your facility. So kind of high level, what's in the reports for water plants here, what we're focusing on today. We have a benchmarking table in there that shows whether you're a surface water plant, there's different benchmarks than if you're a groundwater well plant. So we compare your plant against the appropriate benchmarking data, let you know where you stand. We kind of provide a process overview, so we make sure we're tracking all the equipment that's in place, go over any known issues, what you're doing well at your plant, give you kudos for any energy conservation you're already performing. We try to incorporate that all into your report so that this, if you do end up sharing this report with other people within your municipality, mayor or someone like that, they can see you're already doing good work. They can see justification for new work that you want to do. That can help drive some of these projects forward. During the assessment, when we're walking through your facility, we're going to stop, look at your SCADA system. We're going to be taking a lot of pictures. Many times it's a few hundred pictures per site. So we get a lot of information, all through pump information, equipment, things like that. We're going to ask a lot of detailed questions, try to figure out what issues you have with existing systems. Are there things you want to try to remedy? How is equipment being used so we can better identify energy use patterns and things like that and incorporate those into our analysis. And then our energy assessment reports, once we generate those, you get a nice cover page, some details on your facility, who to contact, who worked on your report. The first thing in there is an executive summary of all the savings that we identified for your plant. And then later in the report, some detailed information where we talk about existing conditions and operations and suggested remedies or changes that can help save you some energy. So I'm going to kick things off today talking a little bit about VFDs, and we'll turn it over to Matt Johnson to talk a little bit about his experience with field implementation and working on the contractor side. And then Don Jensen will finish things off for you. We all know you like to hear from fellow operators. So the first thing For VFDs, why are they so popular? The pump affinity laws. For 50% or 20% reduction in speed, you can get about a 50% reduction in power. A 50% reduction in speed is like an 80% reduction in power if you're looking at just the pump affinity laws. So why don't every single pump that we have a VFD on it? Well, sometimes there's conditions that arise where these affinity laws don't exactly play out like you would think. And that involves looking at how your system interacts with your pump curve. So what we're showing at the bottom of the screen is just the energy trade-off. If you're doing typical throttling in a system, you're increasing the head pressure to decrease the flow, but that still maintains a high energy consumption rate for your system. When you apply a VFD to that instead, in many situations, you're going to see significantly more savings than if you're trying to throttle the system flows. But something to be aware of, if you're reducing the speed of the pump, you get a straight reduction in flow rate. The square of that is your reduction in pressure output from the pump, and the cube of that is the reduction in your power consumption. So something to be aware of when you're looking at these systems is to understand your VFD potential. If you can look at your system curve and compare it to your pump curve, if they're relatively flat to each other, as we're showing in the top right corner here, there's going to be limited savings potential, if any at all. What happens is you start to slow the pump down, it gets into an uncontrollable range where a small change in head pressure and speed creates a large change in flow and just becomes an uncontrollable system. So in general, if you have a steeper system curve, you're going to have more applications for VFD at your site. Some things that you can think about in your system is if you've got a short run of pipe length with a high static lift, that's generally going to be a flatter system curve. If you've got a longer run of pipe to a distant water tower, or you're drawing from a surface water body that's farther away from your plant, the longer that pipe run in is, the more adjustability you're going to have in your flow rates, the more applicable a VFD is going to be to that kind of system. So what we're showing here is for the same design condition on these charts where the green and blue pump lines cross at 100% speed, those are both 400 GPM at 54 feet of total dynamic head. So this is a relatively shallow application here, not a lot of static head on this system. But the top one, you've got a higher static pressure with lower dynamic pressure change rate. So this would correspond to a deeper well with a shorter pipe run. You can only really slow that motor down to about 10% before you're getting into an uncontrollable range, maybe less than that based on these curves. Where the bottom application, you've got slightly lower static pressure, so slightly shallower well, surface water body, something like that, with a longer pipe run. So that system curve is a little steeper. So you got more ability to slow down your motor. You got more savings potential in this situation. But there are cases where if you've got a shallow system curve, you can look at a steeper pump curve. And so you might have to swap out your pump, but you can open up the potential for more VFD savings that way. So at the top right here, it's the same system curve as we had on the last page. It's a little shallower. The bottom picture is the same system curve, but with a steeper pump curve. And you can see there's more potential for that VFD to slow down on the system and provide a little bit more controllability. So there are options you can look into, even if you've got a shallow system curve. They can give you a little bit more controllability with a VFD. But it does involve swapping out the entire pump system and not just installing a VFD on your existing equipment. Some benefits for VFDs on the raw water side of your systems. If you're drawing from wells, if you're slowing down how much you're drawing water out of that system, you reduce the drawdown rate around your well. So as you're drawing water out of the ground, right around your well, the surface level of that groundwater drops down. And that increases the static head on the system. So if you can slow down the rate that you're drawing water out of that system, that surface level doesn't drop as much. That provides more assisting head. You can back off the energy needs on your pump a bit more by doing that. You can also extend the well life between cleanings by doing something like this, because you're not drawing water as fast through the aquifer, so you're not clogging up the filters and bed material around that with smaller grains and things that can clog that system up. So you extend the operating life of your well between major cleanings and things like that. You also have the ability to match that raw water flow rate to any demand changes on your system side. So you can match your raw water coming into the plant with what demand is going out. You reduce wear and tear on the pumps, so you extend the life of your equipment, the motors, and things like that. And one application that we kind of see where VFDs are really effective for well pumps is if you've got an oversized pump where the demand just hasn't grown for your community that was projected. You've got a motor that's twice the size, twice the flow of what you actually need. The VFD can provide some savings by backing that flow rate off. On the high service side, if you've got a closed loop system where your pumps are maintaining system pressure, VFDs are a great opportunity to provide some pressure modulation and demand matching on your system delivery side. And they also provide a way to, if you're changing between pumps because of varying flow rates or trying to match system demands, you reduce pressure transients that can cause water hammer, and those can cause leaks out in your distribution system. So there's a great opportunity there, and really a specific application on closed loop systems. For tower and gravity pressure systems, we see a little less applicability with VFDs because they're charging up a tower. There's a really high static lift. Usually the tower is not very far from the pump station. And so in many situations, a VFD doesn't really align well with water towers unless they're far away from the plant facility and pumping facility. But what you can do, and what we do see some people doing with VFDs, is they'll do a seasonal mode switch where in the wintertime, you don't have as much demand as you have in the summer. And so they'll have a summer set point of higher flow and then a winter set point of lower flow. And they'll just seasonally switch between those two settings on a VFD to get some motor savings in the wintertime when they don't have as much demand. And then also, again, if you've got system delivery pumps that at higher flow rates, you use one pump, at lower flow rates, you use a smaller pump. The VFD can provide a smoother transition between those that, again, reduces those pressure transients, reduces that water hammer potential, reduces leaks in your system, extends the longevity of your distribution network. So with that brief overview and kind of quick high-level look at VFDs, I'll turn it over to Matt Johnson to talk a little bit more about the nuts and bolts.
Thanks, Sean. Okay, so Sean covered a lot of that information pretty well here. I believe he went through about just about all these VFD uses. The one thing I'll maybe add is VFDs can also be used for phase conversion. On most treatment plants, you do have three-phase power, but if you have maybe a booster site elsewhere with single phase, you can use a VFD to boost that up to three-phase to run three-phase motors. We'll look at a quick example here of one of the most frequent uses of the VFD and how it benefits, and that's just to adjust your duty point. So Sean was talking about the static head and the system curve. And so most systems won't have just one system curve. As water levels between tanks rise and fall, the system curve will shift up and down slightly. That's going to change the operating point with the pump. So the pump and the system curve are always going to operate where the two intersect. So at high full sump, you'll have a lower duty point, and so lower head, more flow. And as that water level in your sump drops maybe, then you'll be pumping it higher up and your flow will reduce. It'll shift over to this other point. If that varying flow rate is a problem for your system, then that's where the VFD comes in to actually use the affinity laws to change the pump performance. We can't change the curvature of the system curve because that's based on all the piping and all the valves in place. And so that's not changing in the system. But if you add the VFD, you can then reduce the pump curve to the 55 hertz curve here. And now you have a new intersection between those 2 points, which matches the 500 GPM that you were looking for. Now, Sean used the term in one of his charts there, electric use intensity, where you're comparing the energy use in the plant to a fixed volume of water. Now, you can use that exact same number in individual pieces of equipment. And so for pumps, what we look at is specific energy, which is the unit of energy used over volume of water. Typically, you'll be looking at kilowatt hours per million gallons. And this equation is based off of, well, it simplifies down to the head, pump head over efficiency times the density of the fluid, gravity, and a few conversions for units. So you can actually use these this equation here to figure out how effective a VFD will be at helping you reduce your energy consumption and reduce your specific energy. So you can use that VFD and do two things. You can adjust the head of your system, the H up here. So you want to reduce the head, or you can increase the efficiency. Efficiency is on the bottom of that equation. So if you increase that efficiency, you are decreasing your specific energy. And here's a couple curves similar to what Sean showed, but we'll kind of relate that to specific energy. Now we have a single pump curve here shown with variable frequency options. And then there are 3 different system curves. Each system curve has different slope to it. S1 here would be similar to the water tower application, where you are lifting that water up a certain height. In this one, it's 12 meters. But then as you're pumping more and more water through it, there is not a lot of friction head. So it's increasing very gradually. But because most of this flow is from lifting, slowing it down, you are not decreasing that head very much. So what you'll see up here is the specific energy curve for that application S1. On the bottom, we have frequency. And then on the left, you have specific energy. So at 50 hertz here, as soon as you start moving to the left, your specific energy is rising. So you are not benefiting at all by reducing that sort of curve with the VFD, as Sean said. System 2 here is a little bit less lift, some more curvature. So that's saying a lot of that head, or more of that head, is based on friction loss in the piping. So when you slow down velocity, slow down flow through that piping, you're reducing this head buildup. And as you can see here in the specific energy curve, as you go from 50 hertz down to about 38 hertz, you are decreasing your specific energy there. So you do get some benefit with the VFD. Going from 0.6 kilowatt hours per volume of water down to 0.05. Now the third system curve, it has low lift, and majority of this head here, about 75% of that head, is from friction losses. So as you are decreasing this, you'll see that you're staying pretty close to this 80% line here. This is the efficiency of the pump. You'll see you got 60%, 70%, 80%, and then it goes back down. So your peak efficiency is kind of between these two curves. But in the S3 system, you see the head is decreasing, but your efficiency isn't changing at that same rate. The efficiency is staying high. So you're getting best of both worlds there. You're decreasing head increasing the efficiency, which allows you to reduce your specific energy all the way down to 22 hertz or so. That's like your most efficient spot with that pump and this system. So if you're okay with these flow rates down to 22 hertz, then the lower you can run, the lower specific energy you'll have, and the better you'll be with that in that system. We'll look at just a quick example here on a 2-pump operation for a water recirculation, so a kind of a closed loop system. And in this particular system, let's imagine they need to be able to hit 8,000 GPM, but the average is 3,400. So they have 2 pumps operating in parallel and a piping system that goes from a 14-inch feeding both the 10-inch pumps and then discharging in a combined 14-inch line. So with one pump running, you have that total flow going through that 14-inch, and then it goes through a single 10-inch and then out through the 14-inch pipe. So with that volume, you have a slower velocity in the 14-inch line, and then it increases in that 10-inch line. So that higher velocity is going to increase your friction losses going through this 10-inch section. Now, let's say you turn both pumps on together. Now that flow is splitting between the 2 10-inch lines. You have less volume going through each of those. And so you have less friction loss in these smaller sections of pipe. So you essentially have a system like this, where you have no static head, you're just recirculating water. And then you have a duty point here with 2 pumps to meet your peak demand. In this case, it was about 6,000 GPM. But if you want to look at just one pump running, this intersection point for the 1 curve is not entirely accurate. So we need to actually have 2 different system curves here. One with the water splitting between the 2 pumps, and then one with the total flow going through that half section of the system. And so obviously the intersection of these curves with the pump curve is the best efficiency point, or is where you're operating. So if a single pump here is operating by itself in this curve, this is the point where it's going to run at 3,400 GPM. And you can see we're kind of pretty far to the right of the best efficiency point. Now, if you have the 2 pumps operating together, you have this output here, 57,884 gallons per minute. But each of these pumps operating here is actually a little bit closer to that best efficiency point. So a little bit more efficient with the 2 pumps running. So your 2 pump system point and your 1 pump system curve operating point. But like we were saying before, you don't always need that 6,000 GPM. Let's say you just want to operate at the average 3,400 gallons per minute. Now that 1 pump will do that. Running 1 pump, you're going to get the flow rate that you want. But forcing all that water through that single side of the piping, it's actually working at a head of 10 feet to get that flow rate. Whereas if you are running 2 pumps and you ramp that down to 35 hertz, each pump at 35 hertz, you're getting that same flow rate, but you're not building up that head. So you're getting the flow, but you're using less head. And as we know, a key component of the specific energy is head. So if we are reducing that head, the other thing is the single pump point, like we said, is way out to the right, away from that best efficiency point. When you're operating at 35 hertz here, we trace that over to the single pump 35 hertz curve, we are much closer to that best efficiency point. So we're reducing the head, increasing efficiency, and therefore decreasing the specific energy, operating two pumps at lower speed compared to the single pump by itself. And here you can see that the 3400 GPM, these are the two curves representing specific energy. So one pump with that flow, you're at 60 kilowatt hours per million gallons. Two pumps operating at that flow rate, you're about 25 kilowatt hours per million gallons. So specifically here, you can see the two different operating points, potential, the reduced head, the total efficiency. The total efficiency is increasing. And then that should be 10.3 feet versus 4.8. But your head is decreasing, efficiency increasing, and your specific energy, comparing the two scenarios, it's quite a big difference. So, and if you take that specific energy and you calculate that over the year, for the one pump running at 60 hertz for 3400 GPM, you're going to use about 107 megawatt hours for that full year. We have the two pumps operating at 35 hertz, outputting that same flow rate. You're only using about 47 megawatt hours for the whole year. So a difference of about 60 megawatt hours making that adjustment. So if you do have a scenario like this, it's worth investigating the benefits of operating two at a lower speed instead of a single pump at full speed. And the last thing I'll talk about quickly here is selecting your pump in the application. When we were looking at that slide before, each one of those three system curves operated to the left of the best efficiency point. So automatically, every time you're slowing it down, it is getting less, the pump is getting less efficient. If you are using a VFD, it's important to find a pump where your operating point is to the right of the pump best efficiency point. That way, as you are slowing the pump down, you're actually getting more efficient. So you are moving through this window here where you're getting closer to the best efficiency point, and then you're moving away. This curve here has a specific energy curve on it. So you can see at full speed what the specific energy is. And then you can see it decreasing as you're moving further to the right here. And it's highlighted right here at 34 hertz. That is your lowest specific energy. So that is the most efficient point to operate the pump in this system here at 99 kilowatts per million gallons versus 202 kilowatt hours per million gallons at full speed. So you'll get the most use of your VFD, the most turn down, if you select a pump that operates to the right of its best efficiency point in that system. And I believe now we could pass it over to Don.
All right, let's see if I can figure out how to share this thing. There we go. Just a little bit of background. I am not an engineer. I'm a water plant operator that moved up through the ranks. My degree's in biology, and what I know about VFDs, I learned the hard way. So I manage water treatment plant in Highland Park, and yep, here we go. Just north of Chicago. We serve 30,000 people in Highland Park and another 30,000 in neighboring communities. We're 24/7 operation at Lake Michigan source. Initially, the city was served by artesian wells back in the 1800s. And that there's a steam powered pump station down the lakefront that served the community. They did not, there's no treatment at that time. And of course, it was back in the era of cholera and typhus epidemics. So in the 20s, The plant that we currently have, the initial plant was built in 1929 and incorporated conventional surface treatment technology. Produced and designed to produce 7 million gallons per day at that time. The pumping equipment then was 4160 volt equipment, and that was upgraded in 1960. They doubled the size of the plant, and also got a brand new high-tech control system, as you'll see there on the left, and the hydraulically operated filter tables. That increased, as I said, the plant's capacity to 14. We then modified it subsequent years to get it up to 21 million gallons per day. That occurred in 1986 when I came on board here. We replaced a number of the pumps and converted to liquid chemical feeds at that time, and installed a very early version of SCADA system using mini computers and two 20-inch CRT screens. We just in 2013-14, we converted to ultrafiltration. This is the MEMCOR, this was US Filter, and then Veolia, Vivendi, Siemens, Evaqua, and now it's now DuPont FilmTech. That increased our rated capacity to 30 million gallons per day, and resulted in some surplus space, which someday we may have to use for PFAS. We don't know yet. Granular activated carbon, perhaps the old filter beds. And this gives you an idea of the change in energy requirement when we did convert from the conventional filtration to the membranes. We're producing the same amount of water. Obviously, our service area didn't increase. In fact, over time, we've seen it decrease. You'll see that in an upcoming slide. About 1 to 2% per year decline in water demand, which is not uncommon for water utilities across the country. But we saw about a 30% increase, which is not surprising because there's a third stage pumping required in the ultrafiltration system. We pump it out of the lake with raw water pumps into filtration, the basins or the cells where the fibers live. And then we have a vacuum pump that draws the vacuum on those fibers to deliver it into our clear well and then out to the distribution system. So that vacuum stage is a third pumping stage we've had to add. There are other demands. We use blowers to take the fibers, big blowers, and a lot of air pressure to operate the fibers as well. So there's a lot of additional demand in terms of power. And this illustrates a long-term decline in water demand. And you can see that there's obviously there's an inverse relationship between rainfall and water demand on an annual basis, but the long-term demand is trending downward. We don't know where that is going to flatten out. Obviously, there's a minimum sanitary demand. We are a relatively affluent community here with quite a number of lawn irrigation systems, and so we're always going to see some of that seasonal stuff. But as people buy new laundry equipment, dishwashers, shower heads, toilets, you're going to see a decline in demand over time. As far as the plant statistics, our electrical budget is just around $500,000, probably going to be more closer to 600,000 this coming year with the way the rates are going up. We maintain approximately 100 PSI at the plant. And the reason we're so high is because we're at the foot of about a 60-foot bluff. So to get to our first customer, we've got to overcome that grade change. And again, our water demand has dropped over time. We have a fairly complex distribution system. As Sean mentioned, the closed system is how ours operates. We take water out of the lake, deliver it out to a number of wholesale customers. About half our water is wholesale, so we have to generate enough pressure to deliver it to all those folks. And luckily, once we overcome the hill here adjacent to the plant, it's relatively flat to deliver it out to those folks. So we don't have to boost it. We do have boosting at that north side reservoir for diurnal peaking if we need to. We also have the ability to pressurize the system from there in the event of loss of capacity of the plant, which happens from time to time. We have intake icing events about every couple of years that limit our ability to draw water out of the lake. And so it's awful nice to have that storage available for us. The original, when I came to work here in 1986, we had no VFDs. The way we operated to manage pressure, again, a closed system, we have a tower, but it doesn't float on the system. Hydraulic gradient of the system is well above the overflow of the tower. It initially in 1929 did float, but it hasn't for many, many years. And so we have a little pump up at the tower to draw it down every 3 days to turn the water over and keep it fresh. It does function as a emergency pressure source in the event of a pump failure at the plant, power failure, that sort of thing. So the way we managed pressure in those days was to switch between different sized pumps. And again, as Sean mentioned, that can bounce your system pretty good, unfortunately. But that was the way we were able to change to match pressure. And then we could bleed pressure from trim the system by bleeding pressure into raised reservoirs out in the system. As far as VFDs, we finally installed those in 1994 on 2 of our 6 finished water pumps. Those have since failed us, and we replaced those. We still have 3 of our 6 high surge pumps are soft start. They're not cross line; they are soft start, and we have very slow acting ball valves to try and minimize impact on the system when we start and stop those pumps. Our raw water pumps are also VFD. However, we're not able to quantify the energy savings. We still produce the same amount of water, generally speaking, at the same pressure. The beauty of the VFDs is just to match production to demand. And it's a little bit nicer in the system when you turn those off and on. And you can see that the operators prefer those, obviously. The Hylos 1, 2, 3 get almost 0 hours. 4 and 5 had the VFDs. We recently installed the VFD on number 6, and now he's getting all the time. And that's not surprising because it's really hard to match flow to demand and maintain pressure otherwise. Again, this repeats what I just said. We can occasionally operate if we need more than 1 VFD pump can produce. We will start a second one and run them both at lower speed. The way that we operate these things, just a snapshot of one of our SCADA screens. We have a SCADA rig so that we can do what we call a pressure track. And what it'll do is it'll try to maintain pressure at whatever set point the operator chooses. He'll turn it on at a given pressure, and ideally somewhere mid-range of the VFD, which is typically 55 to 60 hertz. You get below 55 hertz and they're not doing as much good. So they'll set it in that range, and it'll try to maintain pressure when he's operating a single VFD pump. Curves for the engineers in the audience here. Those are typical of our pumps. The pumps were already here when we installed the VFDs, so we didn't select pumps to match the VFDs. And as I mentioned earlier, we sit at the bluff of a 60-foot or at the base of a 60-foot bluff, so we got to overcome that with our pressure before our first customer. Affinity curves, an idea of what we're able to get out of these pumps, and at various speeds with our standard pressure of 98 psi leaving the plant. And we found out the hard way when we first got the first VFD pumps in 1994. We had 0 experience with those. I had none in my previous career. I mean, I've been in water 4 or 5 years before that. And we thought of those as kind of like a light dimmer. You just turn it down and up and get the flow you want. And of course, it doesn't work that way. We learned about affinity curves the hard way. And it actually snuck up on us. An operator would be operating a VFD pump and producing water along with one of the across the line guys. And as system demand slackened off, or someone closed a valve to fill one of the system reservoirs, our customers' reservoirs, we would experience an increase in pressure, and found that the that the pumps were, the VFD pump was actually not only not producing water, it was actually forcing water through it backwards. When he turned the pump off, the station flow increased with the remaining cross the line pump. So that was kind of a hard lesson, but happily there was no damage to the pump, and we've since instituted in the SCADA a warning to the operators in case they accidentally back into that situation based on the pump speed and current. It'll give them a warning. And we've tried really hard to reduce our energy consumption here. We've participated in some of the sponsored programs through Commonwealth Edison. And unfortunately, we weren't able to identify any significant savings. That I guess the good news is we've already picked all the low hanging fruit. We also participated in an energy challenge through the American Water Association a few years back. And I was interested in Sean's mention of benchmarking. I wonder if you're using the benchmark that those of us at the Illinois Section American Water Association identified in 2010, and we're currently in the process of renewing that energy nexus, identifying the energy component in water produced at water plants. That concludes my slides, and happy to take any questions. And I will turn it back over to Cassie.
Thank you so much, Donald and Matt. What an interesting, I love, Donald, the history of the plant. The photos that you showed of the state-of-the-art system was really neat. So I really appreciate that. And thanks for participating in so many of those different programs too. It's really interesting to see, you know, you've already tackled a lot of the low-hanging fruit, and that there are more opportunities, maybe that are bigger, much bigger investments for the plant. I in that cliff or the bluff down from Lake Michigan, because you're right on Lake Michigan there, that creates a lot of pumping pressure that's needed. So thanks for, and I see Bill put some information on the chat about different sorts of incentives. So those resources are available as well. And thank you, Matt, for digging in a little bit more on pump curves, doing explanation. That was really helpful, I think, for a lot of folks. And I think the first question's actually for you, Matt. I will kick it over to you. And if anybody has any other questions as well, please feel free to put them either in the chat or in the Q&A box for our speakers. So the first question is, should I adjust my VFD so I stay close to my total dynamic head of 250 GPM while pumping, but still be able to fill my tower for the tower to exchange water between on and off cycles? Matt, do you think you could field that first question?
Sure. So when you are filling your tower there, you're pumping it straight up. There's a lot of height, but there's not a lot of friction loss to it. So it's going to be very similar to the curves that Don showed, where his curve was extremely flat. And so as you're reducing the speed, you're not able to reduce that head component, but there is potential to increase your efficiency. Every time you have a reduced speed curve, that efficiency curve and that best efficiency point changes a little bit. So really your option would be to kind of reduce it and try and increase the efficiency by moving to a better part of the pump curve. Now you're probably only looking at reducing it a couple of hertz, but if it's a consistent application, like filling the water tower every day throughout the day, then you will see the energy savings over time. So really focus on the best efficiency point of your pump and trying to get as close to that as possible when adjusting the speed.
And we have been to plant facilities that have VFDs installed for filling water towers. And it's that seasonal adjustment I talked about before, where they know in the summertime, they can send a constant flow rate to the tower. It'll draws down a little bit during peak usage and then fills back up during lower usage in the afternoon and evenings. And then the wintertime, they've got a different flow rate that does the same thing. And they just flip between those two VFD settings for their flow rates. And so that is a potential application that can avoid having to install a smaller pony pump or something on the system to do the same thing.
Awesome. Thank you both for addressing that question. Looks like we don't have any other questions in the chat right now. Sean, do you have any questions for our speakers?
I do not have anything off the top of my head. No, Matt covered a lot of the details pretty well, and Don covered the details of his system pretty well with the flat system curve and kind of minimal adjustability to that system, but some significant savings potential there.
So Sean, did you use our Illinois Section Nexus as your benchmarking measure, or is that, I'm seeing Cassie shake her head.
I'll let Sean answer that.
I would have to open the report and look at the footnote real quick. I will let you know.
No, that's all right. I'm just curious. We've been working. COVID kind of interrupted that, but I sit on the Water Efficiency Committee, and we're reprising that study, and it'll be interesting to see if it's changed in the last 12 years. But that was actually referenced nationwide. We were surprised when we did that back in 2010. It was used extensively.
We use a couple different sources for the benchmark. One was a national survey, and one was an Illinois specific survey.
Yeah, that's a challenge, because you've got, as you pointed out, you've got groundwater and distribution only, a lot of Chicago suburbs, and so the energy investment is all over the place.
I'll add some commentary on.
Go ahead, Matt.
So it's easy to plan for use of a VFD and design a system and a pump for use with the VFD. But a lot of people that have systems in place and they don't know exactly how they're going to benefit from a VFD, it helps a lot by, obviously you'll have a pump curve, but you may not know exactly where on the curve you're running. And so you're going to need to use like a pressure gauge right on the pump discharge to help you identify roughly where in that pump curve you're operating. And if you see you're operating to the right of the BEP, to the right of the best efficiency point on that pump, then you do know that as you reduce speed, you will be able to increase the efficiency no matter the application, and slow that pump down and reduce your specific energy that way. So just knowing that you're on the right side of the curve and figuring that out lets you know that there is some potential savings to adding a VFD to that system.
Well, yeah, Matt, from the operator's perspective, they get a little bit of training on pump curves. It's just a tiny bit of what they learn in their formal training, and that's a challenge when we get new operators here. They may not have a clue how to read a pump curve. I didn't when I first started the business, and so translating that into your hieroglyphics you showed us is probably interesting to engineers, but not necessarily to the new operator. And so putting that in terms that a new operator understands is really important. And I'm sending 4 of my staff to Joliet Thursday for an Illinois section pump class. And it's a challenge. It really is, to get people to the point where they really understand what they're doing when they have change speed in a pump or start a second pump or the pressure changes in the system.
Definitely, and there's a lot of organizations and pump suppliers that can offer those basic kind of training courses on how to read a curve and what's the minimum stuff to kind of know to be dangerous, or know that there's potential opportunity to look closer at with someone more knowledgeable potentially.
Well, our challenge here is you look at system curve, and they're different too, and that's the thing. It's really plant specific, and so if I send folks off to a school, they're going to get some information, but it's not directly applicable here, and they're going to have to try and figure out where they are on our system curve as well as they adjust speed on our pumps.
Well, we've got a flurry of questions coming in. So and I love it. So a better application would be on the low service pump side going into the treatment process. Is that correct?
It's situationally dependent, as most of these projects are. For surface water, if you're right next to the lake and you're not pumping up a 90-foot bluff, probably a pretty good VFD application there if you don't have a whole lot of lift. If you've got a 200-foot deep well with, the water table's only 100 feet below the surface, you're still lifting 100 feet there and then pumping 30, 40 feet into your plant. The VFD is going to have limited applicability there. So it depends. It's the sad answer.
Okay, thank you for answering that, Sean. So this person had a follow-up question on that tonal dynamic head question about pumping and then filling the tower. Would running both pumps at lower frequencies be more beneficial rather than one at 2 or 3 megahertz lower?
Potentially. You'd have to definitely look a little bit closer, especially when you just have that minimum adjustability in there. You may not get the trade-off with head and efficiency that you really need to get that benefit. So you'd have to look at it closer.
Yeah, and to that
Unfortunately.
point, thanks, Matt. To that point, feel free to reach out to us. Sean, if you could put your email address in the chat. We have some technical service opportunities that if you want us to take a closer look into that, we certainly can do that for you.
I can just put our information up on the screen for everybody.
Yeah, well, thank you for your questions though, too. This one now is for Highland Park for Donald. Do you have a master plan for plant upgrades, expanding services to other suburbs or additional treatment? And second part to that, so do you have a master plan? And second part, do you foresee an increase in user rates?
Okay, the first part, master plan, we just spent 30 million bucks in 2014. They're not going to give me a lot of money for a long time, although we're working on some grants right now that probably won't get, but we're trying. I want to do some shore well and intake work on our lake intake. That's the one piece we did not do with the upgrade. You've always got to sacrifice something. You're not going to get everything you ask for. The treatment process, we're pretty much state of the art right now with the ultrafiltration. I don't see any need to change that. As far as service area, we're pretty much built out. Some of my wholesale customers have potential to expand their to develop some vacant land in their jurisdictions. But beyond that, no, we sit between a couple of regional water authorities, Central Lake County Joint Action to our north and Northwest Water Commission to our south, that serve some of the inland communities to our west beyond our service area. So no, in terms of water rate, man alive, my chlorine cost went up about 200% in the last year. My chemical cost used to be about a third of my electrical cost. It's now going to be about the same as my electrical cost. Phosphates are crazy. My blended phosphates for lead and copper. So yeah, we're going to have to probably do a rate increase, which is a challenge for us because of the budget cycle and our obligation under contracts to notify our wholesale customers about 4 or 5 months ahead of the end of the calendar year. And these rate increases that all the chemical costs just hit us after, of course, we'd set the rates for the following year. Electrical rates have gone up a lot this year, like 30%. Are just the commodity portion. I don't know what ComEd's going to do. So yeah, we'll have to increase rates just to meet our costs.
Thank you, Donald. All right, and last question that looks like it's in our Q&A box, which please feel free to add more as you have them. We can stick around for a couple minutes after, but are VFDs as beneficial on sludge transfer pumps and sludge mix pumps in wastewater applications? I know this was focused on water treatment today, but we have a wastewater question here. Sean or Matt, would you like to take that question?
I could jump in. Wastewater is our my primarily applications that I work with. Mm-hmm. So sludge pumps they can definitely benefit from a VFD use. Oftentimes you are simply pumping that around the treatment plant. So there's not a lot of elevation change. So a lot of that the head that you see is dynamic head. So as you decrease the flow, you're decreasing that the velocity and then in the head. So there's a lot of specific energy saved. As always, it's pump specific, so you have to know what the limits are and where you need to stop and where you're not improving the specific energy any longer. But the other thing about pumping wastewater is you have to be mindful of the velocity in the piping. So if you slow it down too much, where you're getting flow rates below 3 to 4 feet per second, you can start see the solids in that wastewater start to settle out in the pipeline. So what you would have to do occasionally if you're running at flow rates that produce velocities below that is once a day run at full speed to get that higher velocity through the line to kind of scour and lift up those settled solids and keep them moving down the line. The sludge, oftentimes sludge is recirculated a lot just to keep it moving through the tank to mix it in the tank and even pump it through heat exchangers. So that's just like the example we were looking at before where there was no head. And so you do see a lot of benefit by maybe running 2 pumps in smaller lines that reduces that velocity and that dynamic head part of the curve. So definitely a lot of opportunity there. Worth a discussion with the pump provider.
Awesome. Thank you, Matt. Okay. Let's see. How good are, got another question. How good are VFDs on wells with 10 horsepower motors? This is a good question. Sean, I know you might have done some modeling with this in the past. Or Matt, if you have any responses as well, please feel free to chime in.
Again, it comes back to it's pump and system specific. So it's without having those kind of details, it's hard to know for sure. When in our office, we can usually get access to the pump curves. If we have your pump model number, we can go to the manufacturer with that, get a pump curve. The trick is figuring out what the system curve is. So we're usually trying to get a hydraulic profile, what your pipe diameters are, information like that from the operator. And sometimes it's missing. And so all we've got to go on is what the current operating point is, what the design operating point is, and hoping that those align somewhere on the same system curve. And that's kind of where we do a lot of our analysis is with those assumptions. So I hate to leave it at that again, but it really does depend on the situation.
And please, again, reach out to us if you want us to take a look at applications of VFDs on those various pumps. We can definitely take a look for you.
Mm-hmm.
Bill has a question here. Would a good rule of thumb be over 10 horsepower with variable operations, but running over 2,000 hours a year?
So maybe the concern here is with such a small pump with low power consumption, you may not have the payback in cost and adding that VFD and then seeing that energy savings because it is such a small pump. And that is a possibility. You can look at your life cycle cost to see what the actual energy benefit would be to adding it to that system. But it's definitely worth looking at. Every little bit helps when you're combining all that to your total plant or your total water system electric use intensity.
Matt,
So
that brings up a question that I've had that I should have asked. VFDs are not zero-sum devices. There's some heat generated, there's some loss there. Is there a rule of thumb for percentage of loss in a VFD, or how does one estimate that?
Yeah, just like any motor, there is a certain efficiency of the VFD. Good ones are about 96, 97% efficient. You also have to make sure your motors are rated to work with the VFD because of the output is you're kind of mimicking that 3-phase AC current. It can add heat buildup to different motors, so you have to make sure the insulation in the motor windings is the quality to resist damage from that added heat.
Yeah, we're
So-
also cautioned about harmonics too with VFDs on those.
Mhm.
Yeah, you definitely want to be using shielded power cable on your motors, your pumps. It's not always a problem, but when it becomes a problem, it's hard to identify and it's hard to pinpoint why your level sensor is now being funky or something like that, other equipment in the station.
Interesting. And so it always, I love that this comes back down to, what my dad always used to tell me when I was going through school, do the math. Do the math, understand how your system works, do the math on whether it's going to be most beneficial. And to the other question in the chat about 80% of costs covered by the incentive, again, I think it's up to the math and the payback period and the comfort level of the plant and making that investment. So thanks for talking through that.
Yeah.
It's really good to investigate it. And Sean, you want to chime in?
Yeah, I do know that 10 horsepower and 2,000 hour operating limit is kind of the standard for HVAC type pumping systems and low head recirculating type systems, things like that. When you start looking at higher lift systems, you're starting to look at maybe you want to have a 20 horsepower, 25 horsepower motor for that payback to be there, just because you don't have as much turn down capability in a higher head system.
Mhm.
So, I mean, that 10 horsepower, 7.5 horsepower, somewhere in there, and 2,000 hours is really good for HVAC systems and recirculating type systems as a rule of thumb.
Awesome. Thank you. We have one more question here. We've used VFDs and then we'll wrap up. I won't keep our speakers on and our attendees on much longer. So thanks for listening in for a little bit longer. One last question. We have used VFDs at our lift stations to match incoming flow and also to just ramp up and pump the wet well down. Is there an advantage of one over the other? Cost savings, efficiency, etc. Any thoughts?
So you're talking about like a wastewater lift station. There's obviously other benefits of using the VFD. You can use it for actually cleaning out the lift station. A lot of times you'll have floating solids in that won't ever reach the pump inlet, but you can adjust your water level and pump down so you're kind of sucking off debris on the surface. Pumping normally at reduced speeds, you're not getting that scouring rate, so you're in your force main. The VFD allows you to get to that higher velocity to clean out your force main to the plant.
Yeah, I know on the energy side, when we look at lift stations, we're looking at, is there turn down capability and energy savings versus, an on-off control for a lift station. And usually what we're looking at in energy savings wise is if you can put a VFD in there and we've seen some systems do a constant level for that lift station, as long as it's meeting that minimum flow requirement through the piping to prevent settling. If you're letting that wet well stay at a higher level, you're providing more assisting head to that pump, so there's less lift out of that station, so you can get a slightly better performance out of the pump. But you do, as Matt was saying, you have to occasionally draw it down, get whatever's fog, fats, oils, and grease floating on top of that cleaned out of the system. So we've also seen there's optimization programs built into VFDs now, where instead of trying to maintain a constant level in a wet well, maybe it's more efficient to draw it down at a constant rate, or it depends on the system and what you're looking at. So there's different efficiency opportunities there, and it depends on what's installed.
And there are pumps and VFDs that will monitor their operating speed and do that adjustment by themselves. So they are kind of self-checking to make sure they're at the most efficient speed, and they will slow down or ramp up to adjust that themselves.
Yep.
That's really helpful. Thank you. Okay. Well, it looks like we don't have any more questions in our Q&A or in the chat. Does anybody have any final words of wisdom that they'd like to share with our attendees before we wrap up today's session? I know you've shared so many already.
I would just say
Alright.
thanks for the opportunity to speak, and reach out if you have any other follow-up questions.
Sounds great. Thank you. And I will send out our speakers' contact information today if you have any questions. Of course, that's okay with them. So please feel free to reach out and talk further. Please feel free to reach out to our team as well with any further questions. We will send the CEU course number and certificates. That includes PDH certificates or PDH certificates and CEU certificates, as well as the recording and slides from today's session. Again, that will come out tomorrow. So thank you so much, Donald and Matt and Sean, for speaking today. As you can see, so many folks in our audience today thought it was an excellent webinar. So thank you so much for sharing your expertise and thoughts with us today and taking time to talk about VFDs at water treatment facilities. Our next webinar is going to be on I&I and the impacts of energy on your wastewater treatment plant. So join us on April 25th for that event. So I will send that out via email as well. But thank you to our speakers. Thank you to all of our attendees for joining us today. And we will see you next month. Thank you. Have a good afternoon, everybody.